So for our talk today, we have Professor Nathan Laxague, who will talk about advances in polarimetric remote sensing and ocean waves and near surface currents. A bit of a background, Professor Laxague received his PhD in 2016 from Rosenstein School of Marine and Atmospheric Science in 2016. He then worked as a postdoctoral research scientist at Columbia University's Lamont Doherty Earth Observatory before joining UNH. His research focuses on studying fundamental physical interaction between Earth's atmosphere and ocean using field observation and laboratory measurements. And he's particularly interested in studying ocean surface waves and their mediation of air-sea fluxes. He's interested in developing or leveraging the best available engineering solutions for improving in-situ observation techniques. So, over to you.
Thank you very much, Shania. So, as you mentioned, my name is Nathan Laxague. Some of you have had me or have me in ocean waves and tides. So this is definitely the topic of making observations, field observations of ocean waves is near and dear to my heart, which is a blessing and a curse. But okay, so let's start off. I'm going to justify every single word in that title. But first, let's go big picture. Why do we want to measure ocean waves? And so some of you might look at this from a strictly application-focused engineering perspective. Well, they transmit energy, and this can be a problem if you live on a coastline that is particularly susceptible to erosion. This is the UK, somewhere in the UK. So they don't have a lot of land to begin with, so this is a huge problem when they lose it to coastal erosion. This can be a good thing. Some of you are interested in extracting energy from the sea, from the wave, using a point observer, linear observer, something like that. You're trying to extract energy from the undulating surface motions and turn it into something we can use. Maybe that's pumping water from the ocean floor. Maybe that's generating a current. Okay, so my personal interest is in the energy, but it's not so much the energy that we can use to power, a light bulb or something like that, but it is in the energy in the broad sense. So momentum associated with fluid motions, heat associated with the fundamental stuff in the ocean and the atmosphere. Okay, and so I borrowed this graphic from Huey's creative team, and as wind blows over the ocean, waves develop, they grow, they steepen, they interact with one another non-linearly, they modulate the structure of the boundary layer and the adjoining layers, the adjoining boundary layers, and then they break. And it's a nice, happy little life cycle that they have. And in the process of this, they are doing all sorts of things, stirring, enhancing, mixing, magnifying, usually the effect, the magnitude of latent and sensible heat fluxes. And then there's a really interesting feedback effect, whereby wind blows over the ocean roughens up in response, and that roughening will then increase the momentum uptake by those waves and enhance their growth. And then, of course, as they get steeper and steeper and steeper, there's things like airflow sheltering. Anyways, it's a wonderful multi-body problem that is always interesting, and it really is at the heart of the interaction between these great two fluid bodies. Okay, so there's a challenge at the heart of this, which is why I'm talking today, and that is if we want to make a measurement of a wave-like phenomenon or turbulence in the lower atmosphere, upper ocean, our observations are usually point measurements. So it's zero-dimensional in space, and then there's some sort of temporal variability to it. Or, if you're a satellite remote sensing person, you might get a synoptic snapshot. So you fly a satellite over Earth that's got a synthetic aperture radar antenna, and you get this scan, so you get this beautiful 100 kilometer by 100 kilometer image that tells you something about the backscattered power off the sea surface. So you get a moment in time. So you get access to spatial information, but it is a moment in time. Conversely, the point measurement might be a gauge that you stick in the water and you leave for a year. And you get a nice time record, but it is just one of many possible instantiations of an observation you could make. That's a problem, because it's a problem for a couple of reasons. The biggest one is that numerical models do not have this problem. Numerical models can describe whatever you want them to. You can set a domain. There are limitations, of course, in computational power, but numerical models give you a fully dimensional, temporally evolving state. And we need to be able to validate those models. And we can't really do it effectively, in my opinion, if we have a bunch of zero-dimensional time series. You could just throw numbers at the problem and get thousands of wave buoys and thousands of temperature sensors and basically make it so the ocean is mostly sensors. In my view, an untapped or maybe a appropriately tapped opportunity is that to use remote sensing techniques to get a spatiotemporal depiction of the surface. Okay, I'm going to gild the lily a little bit to all on this topic. So imagine that you get a nice fancy spotter buoy, which is a GPS wave buoy. You put it, this is actually a little bit larger than normal. Normally, the things I have in my slides are larger or smaller than real life. This is actually like a 2-to-1 model, or it's larger than it is in real life. Okay, so this will give us a time series of water surface vertical displacements. The Greek letter eta, the N, with a little stretch leg on it. That is our free surface vertical displacement. It's going to be bobbing up and down, and you might make this measurement over the span of, say, 20 minutes. But in reality, this is just one of many possible realizations. So you could put this buoy here, you could put it over there, you could put it anywhere in this flow field or on this free surface, and you're going to get a different record. It should be statistically the same. We make this assumption about the ergodicity. So you have stationarity here and homogeneity there. So really, you can make a measurement anywhere in this domain, and it should be about the same on average. But it's not just, okay, is there persistent heterogeneity? It's, I care about how one patch is changing relative to another. There's a directionality that I'm missing by only having a single point measurement. Okay, so now I tried to justify why we want to make wave measurements, why we're somewhat limited in our point-like measurements. What is it that we actually want? And what we actually want is, I'll give now an isometric view of what I showed before. We want the free surface vertical displacement as a function of position, lateral position, x and y, if you're in Cartesian coordinates, and time. And this is being represented as this sum over some arbitrary number of components, where you've got, for each wave vector and frequency pair, you have a particular amplitude, which I've denoted as eta sub k. And then there's a complex conjugate, so there's a real and complex part. You take the real part to get a real free surface displacement. What I've generated right there is just, I've taken a directional wave spectrum, which I'll get into what that looks like in a few slides. I've taken a directional wave spectrum, and then I've assigned a random phase to each of the components and allowed them to propagate freely in time. And so this is just, I've started with the assumption that I know what's up there, and then I say, okay, let's go to town and generate that. And then the red colors are high and the blue colors are in the troughs. Okay, so if you take a fast Fourier transform, or a Fourier transform of this measurement, this fully spatiotemporal measurement of the surface wave field, you get a wave number frequency directional spectrum. So that here it is in Cartesian form. You have, let's say, x is east and y is north, and then omega, the radiant frequency, is 2 pi over the period, the time scale of interest. Okay, so what we can do is we can integrate that overall wave number and direction, and we get a frequency spectrum. And so for those of you who've taken Professor Lippmann's time series analysis class, which I highly recommend if you have not, fantastic class. I think Fourier analysis is one of the most important tools that a physical scientist has. It might be the most important algorithm ever developed. Anyways, so this is a frequency spectrum. And as I explained to my waves and tide students this morning, this frequency spectrum can be thought of as a scale-aware density function. It's a distribution of energy, not just in terms of how frequent and how often it occurs, but the actual scale of motion in which that energy is being carried. And so this is really valuable because we can look at different spectral subranges, and here computed in log scale, and we can assign, or we can interpret those subrange slopes as being a balance of different physical processes. In this case, this frequency to the -4 power, that gives us a hint that there's a relative balance between wind input, dissipation due to braking, and nonlinear actions between wave modes. Whereas this f to the -5 tail, that tells us that, well, nonlinear interactions aren't really doing much anymore. It's really all about a balance between wind input and braking, or dissipation due to braking. This is somewhat analogous to if you study turbulence and you look for a k to the -5/3 or an f to the -5/3 power law. Power laws are a great way of finding order amongst the chaos. Okay, you can integrate over frequency, and in this case, I'm integrating over positive frequencies. That sounds weird. What is a negative frequency? Well, you get the symmetric you get this symmetric spectrum. If you just integrate over the positive frequencies, then you can resolve this 180-degree ambiguity. And now we can see, okay, without getting too much into what the color represents, it's a saturation spectrum, but it goes like the wave elevation spectrum times k to the 4th power. So really this is emphasizing the structure, the directional structure of the very short wave components. Okay, so we integrate over positive frequencies, and now we can see, okay, as a function of wave number, so scale and direction, where is my wave energy going? How is it propagating? Okay. Let's say we don't want to integrate, we just want to take a slice, say in the downwind direction. Now we have the energy in wave number frequency space. And what varies wave number frequency space? Well, that's wave dispersion. This tells us how fast the features are propagating. And so you could just draw a little red curve on there that would show you the theoretical linear dispersion relation. Those of you who are joining us from Tech 411 don't know what I'm talking about, but that's okay. Someday you might be fortunate or unfortunate enough to learn. It tells us the speed that waves, free surface waves travel at the air-water interface. There's a dispersion relation for many different waves and many different media. Dispersiveness is a really cool feature of dispersion, is a really cool feature of waves that I'm not going to get into too much. But we do exploit it to make, to infer the near surface current from these wave spectra. Okay. So that's a lot of background. How do we obtain this information? How do we obtain something that's not just a point time series, but it is 1,000 by 1,000 point time series, all undulating next to each other, so we can get a fully directional spatiotemporal description of the sea surface? Okay, so one approach is to do stereo, basically do with cameras what our eyes and brains are doing right now, or one brain. So each of us has a certain number of eyes and at least one brain, or exactly one brain, hopefully. Measurements of short water waves using stereo-matched image sequences. This is from Alvisa Benetazzo, who's at CNR ISMAR over in Venice. And the idea is you were looking at a scene with two cameras with a slightly different attitude, and then from that look geometry, you can infer the displacement in X, Y, and Z in Cartesian space of each facet that you're imaging. And you get something that looks a little like this. This is from 2006. More recently, this was packaged into an open source, freely available toolbox called WAS, depending on if you're German, for obtaining the free surface vertical displacement. And it's actually really straightforward, I would say easy to use. It's computationally a bit intensive, but it gives you fantastic measurement of the free surface vertical displacement, which I don't want to undersell this. I think it's pretty cool that you can take two cameras, point them at the sea surface, and not just get a pretty picture, but you get the actual measurement of the vertical displacement as a function of space and time. That's really powerful, I think. Okay. What I'm going to be talking with you today about, though, is called polarimetric slope sensing. And polarimetric slope sensing has been a technique that I've been using for almost 15 years now to study ocean surface wave kinematics and their connection to wind forcing and near surface currents. The basic idea behind it is you measure the polarization state of light reflected off the sea surface, and you can use that to infer the geometry of the actual facet that reflected the light. So think about this: if you ever have Polaroid sunglasses, you look up at the sky, you float your head to the right, you float your head to the left, and the sky looks a little bit different. The intensity changes right before your eyes. What's happening is the radiation leaving the sky has a particular polarization state, and your lenses are polarized in the vertical. There's a 0-degree polarization to them. And so they're going to permit light that has the same polarization. So if you rotate your head a little bit, you're going to now be blocking out certain rays of light, but not others. And so what's happening is you can say, well, if you've got unpolarized light that comes from the sky, it hits the sea surface. That reflection off the sea surface is then going to change the polarization state. We can now invert that polarization state and obtain the free surface geometry. Okay, so I'm going to show you a Stommel diagram. So I think it's a wonderful device. Anytime you're dealing with geophysical flows, you've got a spatial scale on the horizontal axis, a temporal scale on the vertical axis. Things that are small tend to have a high or a short turnover time, and so you tend to see something a little bit like a 1-to-1 or some sort of like positive correlation between these two things, right? In this case, that black curve is the dispersion relation. Once you get to a certain spatial scale down here, now capillarity is the dominant restoring force for these surface waves, and so you get this bend in the dispersion relation. So stereo video is up here in the upper right-hand corner. That gives you scales that are nominally 50 centimeters to 100 meters, and then those correspond, if we just take the corners of the dispersion relation, let's say, 2 seconds up to 10 seconds. It's actually a pretty narrow chunk of wave number frequency space. And then polarimetry, we've got 3 orders of magnitude to work with, a 1 megapixel camera. We can put that wherever we want. Typically, we're measuring waves that are about a couple of millimeters up to a couple of meters, which, if that sounds small, it is. And part of this talk today is going to be dealing with that and trying to improve things as best we can. Okay, so the idea behind polarimetric slope sensing is light comes from the sky, it's got a polarization state, hopefully unpolarized. It hits the sea surface and now has a new polarization state. So we can use the Fresnel reflection coefficients to come up with something called the Fresnel curve, and this allows us to relate the incidence angle of the sea surface facet to the degree of linear polarization. This maximum value is Brewster's angle. It's about 53 degrees for an index of refraction of 1.33, which is what seawater has just about. Okay, and so we construct this Stokes vector by the sum or difference of different polarized light intensity components. Okay, so we just have to measure the intensity of light at 0, 90, 45, and 135 degrees, and we can construct our Stokes vector. Then we can invert this and obtain the incidence angle. Okay, so this is what that would look like. After we run through our machinery, we obtain these two angles, phi and theta, and then those allow us to define this surface normal vector. So we're measuring here, the light's coming in from there, and then this incidence angle that it takes relative to that normal facet is theta. Okay, pretty straightforward. So this is what we get. This is the measurement. So these grayscale images are not just a black and white camera. This, on the left-hand side, is our long look slope component, and the right-hand side is our cross look slope component. The wind is coming from the upper right-hand part of the frame, which is bonkers because there are waves going in every single direction. And this is what the ocean looks like in practice. When you look out on the water, the picture that you see is really determined by your look angle and where the sun is, and you're just seeing one potential realization of it. But if you take all of that bias away, what you get is an extremely multi-dimensional, multi-directional wave propagation state. You actually have short waves that are propagating upwind. They are fighting the near surface current. They do not care. They just sort of glide past one another. They do not interact. They're like ghosts. They pass through each other. There are interactions between short waves, nonlinear interactions, but generally speaking, ocean waves do not, very low amplitude ones do not resonate. They do not interact strongly and exchange energy. So it's a very strange picture. It runs contrary to our idea of how waves should behave and how physical objects should pass, or how they should behave in the presence of one another. That's part of what makes them so interesting. Okay, so the evolution of optical polarimetry really, I'm sorry if this talk is a little bit too nuts and bolts for those of you who are mathematically inclined, but really we, as observationalists, we are captive to the realities of technology, for better or worse. So about 15 years ago, you'd have to spend $300,000 to get one of these sorts of instruments. Actually, the one that I worked with 15 years ago was around $30,000. So you can actually put that in a research proposal and not have a program officer thinking that you're embezzling money. But now they cost $3,000 and they're the size of a walnut. And the detector arrays on them are actually there's these microlithography. So each of these photodiodes is about 3.5 microns. And these little individually printed, finely lithographed filters are able to block out. So basically you'd have an on-chip lens, a polarizer, and the photodiode. So you can make all of your measurements, all 4 of your measurements, on a single 2/3 inch focal plane array. This is pretty outstanding. It used to be that we'd have 4 cameras and a custom polarizing beam splitting path, and it was really a one-off engineering project. Now you can go to, maybe not Amazon, but you can get them through like Edmund Optics. You can go to UShop and buy it and it'll be there in 2 days. It's pretty awesome. Okay, so I'm just excited about that because it used to be such a huge headache. Okay, there are a couple problems with this though, so I'm getting ahead of myself as usual. So we've now increased the amount of area over which we need to make a measurement. So you can think of this as now your effective pixel has gotten larger, which means you're going to be doing some spatial averaging. So imagine that little wavy shape on the top is the wave that we want to measure, and this is the wave that we think we're going to measure. So that's reality, and this is what's going to come out the other end of our measurement routine. The problem, what's going on here, is that we are measuring intensity and inferring slope, but that process is really nonlinear, and so the order of averaging matters. If you measure intensity and you do spatial averaging, that doesn't necessarily equal the spatial average of the slope. It's kind of a subtle point. But we're used to linear operations where you can average before or after, it doesn't really matter. This is highly nonlinear, and there is going to be, potentially, there's going to be some sort of aberrations or penalty that you pay for doing this coarse resolution observation. Okay, and so this, I've just overlaid the degree of linear polarization. The question, does the average of the degree of linear polarization give you the same slope that you would get if you just had a coarser object that you're looking at? And it turns out from some of our testing that we've done is you actually do pay a penalty. So I'll try to interpret this figure as best I can. This violet curve is the ground truth, or that is our full resolution observation. It's about 1 millimeter per pixel resolution. If we do averaging in a 2x2 block, and then we compute a spectrum, we get the teal curve. If we do a 4x4, we get the green. If we do an 8x8, we get the yellow. If we do 16x16, et cetera, et cetera, et cetera. So ideally, these should all fall on top of each other, and they should just be cut off at their new Nyquist wave number. But we don't see that. There is this penalty that's being paid, almost like a damping function. So basically, there are negative consequences for scale much, much larger than the averaging window. This is a problem because we think that we're just doing a little spatial averaging, but in fact, we're affecting scales that are 10 times larger than our effective pixel size. And yes, if you want to learn more about that, you can take a picture of this QR code. This was published, our quantification of this effect, including some numerical modeling of light reflecting off a modeled sea surface. That was just published this year in IEEE Transactions on Geoscience and Remote Sensing. Okay, I'm not going to dwell too much on that, but I will talk about we got more problems and solutions somehow. So two fundamental challenges to the technique remain. I mentioned the one about the focal plane array detector. Maybe it's a solved problem, maybe it's not. There are two ones that are really fundamental. They exist regardless of what sort of camera you pick. And first one I really glossed over, and that is that the sky leaving polarization state is not necessarily unpolarized. You might have a variation in the polarization state of light leaving this nice sunny sky, blue sky, and this overcast sky. It's actually quite different, as you might expect. And to illustrate that, I've run through these Fresnel reflection coefficients. You build these, well, I'm not going to get too much in how you build them, but anyways, you can model the Fresnel curve, how the Fresnel curve will change as you increase the fraction of light that is upwelling, that's non-polarized, that's just coming up through the ocean air-water interface. We know that this is, in general, non-zero when you look out at the ocean, because unless you're looking at a cheap video game where the whole surface of the water looks like glass or a mirror, you're going to have some volume scattering. And so you take a trip on a ferry, and you look and you see little like crepuscular rays of light going into the water, you see backscatter, you see kelp, you see anything underneath the surface, that is going to be upwelling radiance. That is light that is going through the surface, scattering off some stuff, coming back to you. And that is generally unpolarized, or it's weakly polarized, which is basically like putting a wet blanket on your Fresnel curve and really suppressing things, suppressing the response. So you're compressing your dynamic range, you're making the pore measurement. You think when you measure a DOP of 0.4 that you have an angle that is, I don't know, 27 degrees, but in fact, because you had a little bit of upwelling radiance that was unpolarized, you have 37 degrees. And so you have a pretty big error, not just in the the offset, but you're actually compressing things a little bit. Okay. So this extends if the radiation the radiance that is leaving the sky is itself polarized, you're essentially raising your floor. So basically you've got a bunch of polarized light that's leaving the sky, it's going to hit the surface, it's going to reflect, it's going to be polarized. You're not going to have really low degree of linear polarization. And again, this sort of retroflection is a huge problem. I don't even know how to deal with that. We're going to ignore that. Go past this part. Okay. The other problem is geometric in nature. It is really all about the field of view. So we have a limited spatial field of view. And so the benefit of polarimetric slope sensing is that it's very fine resolution. We can access information about waves that were just not available in any other field observational technique, truly. The problem, though, is that we see this wave pass by. So these are, I've taken sea surface slope fields, I've integrated them numerically, and we have actually the water surface elevation, and that the color of that is just one component of the slope. So we have this really nice view of a wave passing through our field of view. Our eyes and brains are pattern matching algorithms. They're really good at finding patterns and trends and things, and we see this wave pass through. There's a crest right there, there's a crest right there, and now it's gone. So we see a wave has passed through. But the FFT, when it's looking at the spatial characteristics of the wave field, it does not give you any of that information because this scale of motion is way outside the domain. You might see a little bit of signature of it in the time domain, but that's a whole other ball of wax. And actually, it is in the time domain, which is how we're going to access it, but it's not in the spatial domain. And so as far as we're concerned with the sort of basic Fourier analysis, it's unavailable to us. So we need to fix that problem. Okay, so I'll go back to my stumble diagram. The problem that I'm talking about is that this is unavailable. We basically planted our flag down here. We're going to content ourselves with dealing with capillary waves and gravity capillary waves and short gravity waves, but we're not going to be able to access any of the stuff that 99% of people who are measuring waves actually get on a daily basis. Okay, even though, I mentioned this in passing at the beginning, the waves that are really responding to wind forcing, if you want to look at, okay, I want to infer wind speed from what the wave state is doing, it's really these short waves. You can get some progress from measuring in the equilibrium range and then connecting that to the wind forcing. But the waves that are actually providing the individual roughness elements and affecting the aerodynamic roughness, those are quite small, say 1 centimeter to 10 meters, something like that. And that is really basically outside the range of these buoys and gauges. You know, we think we're measuring a short wave that's 1 second. Well, 1 second wave is actually quite large in the grand scheme of things. Okay, so challenge. Let's combat challenge number one, this variation in ambient illumination conditions. Okay, so the most crude way of doing this, quick and easy, is to say, well, this unpolarized light is acting like a wet blanket, so let's just pick that wet blanket up. Let's just unsuppress things. Let's basically say, well, I'm expecting to get 0.44 for my incidence angle of 30 degrees. I'm actually getting 0.23. I know what my camera look angle is. Therefore, I can just take the ratio between ideal and observed and use that as a gain, an empirical gain factor. So this is a little bit crude, but what's nice about it is I just need a single camera. I'm looking with a known incidence angle, so I know what the center of my frame DLP should be, and I just boost up every single degree of linear polarization that I'm measuring. And that gives me something like this. So you can see on the left-hand side, you can barely see it on a good screen. When you've got a projector that kind of washes things out, it's really hard to see the detail. On the right-hand side, though, you can actually see the dynamic range. Things have been stretched out a little bit. This is like contrast stretching. But it's contrast stretching that's being informed by the physical constraints of the measurement. Okay, so I'm going to consider that solved. I'm not going to justify it. It would just take too long to talk about what that does to the statistics. So that modifies the downwind and crosswind statistics that we measure, and it affects the skewness and kurtosis, peak, and all of the statistical moments of our slope fields. I'm not going to get into that, but we're working on a manuscript right now that is basically documenting all of this. Okay, challenge number 2, we have a limited spatial field of view. Okay, so remember, this morning, waves and tides students, I wrote down this equation. This is our free surface vertical displacement for a progressive wave in one dimension to keep things easy. Let's take a spatial derivative of that. So now d to dx, that is our along x slope. So we get minus ak times sine of kx minus omega t. So that is telling us that we can now relate the free surface vertical displacement to our slope. Of course, we pick up phase shift. We'll deal with that later. But we've now created a transfer function. So if we measure the slope, we can divide by we can multiply by -1/k and then account for the phase shift, and that will give us our vertical displacement. Of course, how do you divide by k? Well, you use the hammer for every nail, and that is the Fourier transform. You take a Fourier transform of your slope in east and north. You multiply by this transfer function minus I/k, so the I is doing the phase shifting for us, and then we invert the Fourier transform, and we get a water surface vertical displacement. So the dashed curve is the east component of the slope, the dotted curve is the north component of the slope, and the red curve is the water surface elevation that we infer just from those two pieces of information. Okay, there's a little bit going on behind the scenes. Those of you taking time series analysis understand. Anytime you are doing an inversion technique, a proxy measurement, there's a penalty to be paid at large frequencies and small frequencies. You're going to be really careful about what your passband is. So for example, the transfer function goes like 1/k, which is 1 over frequency squared. And so if you've got a small frequency, that's an enormous boost to those energies. And so if you've got a little bit of noise that's creeping in at, say, a 20-second period, so 0.05 hertz, you're going to divide by 0.05 squared, your spectral energy density, which is just incredibly, boosting up that noise. And so in order to make it so that your spectrum doesn't blow up in the left-hand side or the really, really small frequencies, you apply a bandpass filter. You block that out. So this requires a little bit of iteration to find what the right passband is. Okay. On the high frequency part, it's a little bit more straightforward. We're actually just constrained by the geometry of the frame. This black spectrum, we get that from a LiDAR, from a Regal LiDAR that we put off of Air Senior Action Tower, about 3 kilometers south of Martha's Vineyard a couple years ago. And then these 3 different colors, it's maybe hard to distinguish. That is violet, that is teal, and that is red. The red is with the empirical gain. The teal is a laboratory gain. I'm not going to get into what that is, but it's basically saying, can we correct this problem just in the lab? Not really. So the empirical does most of the heavy lifting for us. The no gain is if we just take it off the shelf and assume we're good to go. And the answer is we're not good to go. What happens at about 0.4 hertz? Well, my claim is that this is a point that I made this morning in my Waves and Tides lecture. I'll make it again because we're not all there, obviously. Making a spatial measurement is not the same as making a temporal measurement in that a proper sample is localized in time, but if you have an image, or I guess in this case, you're actually averaging over a 3 meter by 3 meter patch of the ocean and getting the mean surface tilt, you've created a buoy with the world's worst RAO. So it's really not responding well to anything out here, not even a little bit, right? And the way that it's falling off, well, imagine that you're measuring a little bit of the crest, but also some of the adjoining faces of the wave. You're now kind of suppressing that. And so there is this really strong suppression. You would expect, okay, I can just use Nyquist sampling theorem and say, I'm good to 0.8 hertz. Not really, because if your field of view is about 80% of the length of the wave, you're just going to be smashing all of that variation, just kind of compressing that signal. And so you have to be kind of actually aggressive in filtering that out. So long story short, this inversion approach is good, but really only for intermediate scales. Let's say from 12 seconds to about 3 seconds, 3 to 4 seconds, which is still a lot better than what we had before. And to demonstrate the skill of this technique, we ran some statistical comparison of the significant wave height computed from the 0th moment of the spectrum. And we see that, yeah, this empirical gain approach, it doesn't just get the high frequency waves well. When we apply the empirical gain and then run through this slope inversion technique, we can actually get a decent estimate of what the significant wave height is relative to the LiDAR. Of course, standard statistical comparison wizardry, there's a bunch of points lying outside that 95% confidence interval range. But, you know, R squared of 0.75, we've got a pretty decent root mean squared error, a slope that's about 1 to 1, and then a very small bias of about 10 centimeters. And I would say that these statistics are almost comparable to what you would get if you had different types of buoys. So like a hippie buoy, an NDVC buoy, a cloverleaf buoy, a spotter buoy, a directional wave rider, you get a bottom pressure sensor. You can go to FRF and duck and put all these things out in the ocean, and you've got, you know, marketed equivalents of different types of buoys that should give you the exact same information, and no, they give you information that differs actually quite a bit in wave height. But so I think it's not perfect. It's maybe not exactly what we'd want, but it does a pretty good job of getting the long wave information. Okay, so we can do this over many measurements, let's say 200 of them, and we get the frequency omnidirectional spectrum, that's on the left-hand side, the wave number omnidirectional spectrum on the right-hand side. I've used linear theory to convert from a frequency spectrum to a wave number spectrum for the larger scales there, but everything else we get directly. So this shortwave frequency direction or frequency spectrum and the shortwave wave number spectrum, we get those directly from imaging our sea surface slopes. And then that upper left-hand corner frequency spectrum, we get that from the aforementioned slope inversion technique. It's kind of hard to see what is happening at high wave number and high frequency, so we can compensate these spectra. That's what I'm doing here. So this lower left-hand corner, multiplying by omega, or the wave frequency to the 5th power divided by g squared, or divided by g squared. And the right-hand side, I multiplied by k to the 3rd power. So you don't have to know anything about wave kinematics or wave energy flux to understand what's going on here. I will just say in passing that we look for a slope. That dashed line, again, is this equilibrium range. It's a balance between wind input, dissipation, and nonlinear interactions. That horizontal dotted line is a balance between wind input and dissipation. And so I gathered 2 pieces of information from this comparison. One, okay, we see these spectral shapes that match our a priori expectation for what the system should be looking like. And 2, I haven't fudged any numbers. I haven't said, okay, you long wave spectrum, you have to match up with short wave spectrum. Okay, you have to match up there. I haven't fudged, put my thumb on the scale. This is just sort of, I'm saying we're going to maintain consistency between the look angle and what we're measuring and let things go from there. And just naturally, there is this, I would say, pretty good agreement in spectral energy density absolute level, but then also the slope. So that's a very good sign in my view. Okay, wave directionality. I mentioned directionality. Directionality is super important. Let's go back to this little free surface vertical displacement map. We've got our buoy that's floating there. We've now created a virtual buoy. A virtual buoy is measuring water surface elevation, eastward slope, and northward slope, which means anything that we did with that small buoy, with that real buoy, we can do with our virtual buoy. I'm not going to go through the details of this or even bore you with this. Essentially what's going on is you compute the cross spectrum between elevation and northward slope, or elevation and eastward slope, or eastward slope and northward slope, and then you grab either a real component or imaginary component, you do some manipulations, and that phase dependent analysis actually gives you a directional spreading function that you can multiply your omnidirectional spectrum with, and now you know not only, okay, how much energy there is in a 10-second wave, but where is it going? And so this is we generated this from an RDI, Teledyne RDI ADCP that was about 1 kilometer away from our tower when we were making these measurements. The black arrow is the wind direction, so it's coming out of the north east, and then the red is the near surface current, so the wind is going, the current is going upwind somehow. That happens sometimes. Probably a strong tidal flow. Okay, this next panel is this EPSS, this extended polarimetric slope sensing technique. And so we get big picture, similar information. We've got a dominant wave direction. There's a little bit of an offset there. But then at the short waves, we are actually, this virtual buoy-based technique is actually getting that we have these shorter waves, intermediate scale waves that are propagating downwind. Now, when we compare both these pieces of information to what we're getting directly from the slope fields, we see that indeed, short wave information, so this is 1 hertz, this is 10 hertz, so these are very short waves. These are propagating about into the wind direction, or in the downwind direction. We have this is a very strange case study to use, but we actually had long waves that were traveling north and wind that was going, or coming out of the northeast. So you have this very big misalignment between the non-locally generated swell and the local wind sea. And in between, you have this veering effect going on, whereby as waves get shorter and shorter, they turn more and more towards the wind direction. And then we have, plus minus 20, 30 degrees, the short waves are going about into the wind direction. I'm not going to get too much into that little divot in there. That has to do with braking and nonlinear interaction, so that's super interesting. Save that for another talk. Okay, so comparing the two, the estimate from the ADCP and this extended polarimetric slope sensing, we can compute something. This is the spreading width, or it's basically the standard deviation. So what you would do is you would take your wave direction, you subtract the mean wave direction, square it, and then multiply that squared thing by this directional spreading function, which is dimensionless, and it tells the waves how to spread their energy. Okay, and then if we compare that not just for a single case, but over all cases, and we compute that at the energy weighted mean period, so something right around the peak period, we see there's a general agreement in the magnitude and the trend with increasing wind speed. So as wind speed increases, the wave field develops, and if you're at the peak or near the peak frequency, your waves tend to go with a pretty narrow spread. And then that spread increases as you get to higher and higher frequencies. We see that in observational spectra all the time. Okay, and so I'm going to give a quick plug on this. Plan is to submit this thing early next week. In the interest of radical transparency, you can go to GitHub, you can clone a repository, you just run a couple commands, it will install all the Python dependencies, it will grab all the data from the, where will it do that? Did I miss that? Okay, I guess maybe that's borrowed and make data. I think I've changed this since then, sorry. It grabs the data from Zenodo, an EU-funded public data archive. It produces all the intermediate products, it produces all the figures, and then uses LaTeX to compile a finished manuscript. And so you can look at every single step of the process if you'd like to. Okay, so what can we use this for? I've gone through about 40 minutes of background, wonderful, okay. Okay, so imagine you have a wave number frequency spectrum in the downwind direction, and your dispersion relation goes something like this. So the wave energy likes to be along those two curves. If you have a little bit of current, then your dispersion relation looks something like this. And so the waves going downwind are going a little bit faster because they're being carried by the wind drift, and the waves going upwind are moving a little bit slower because they're swimming upstream. And so what you can do is interpret this to infer the current as a function of wave number, and then knowing that the very short waves, the shorter wave is, the shallower current it's going to be feeling, we can now obtain the variation of the current profile with depth. So I'm showing some results that were produced by a collaborator at Columbia University, Jere and Chris Zappa. This is work submitted to Journal of Geophysical Research Oceans, currently under review. This is a current profile where we have a measurement of the viscous sublayer drift from an infrared camera. These open diamonds are the current that is inferred from the Doppler shift of the dispersion relation. And then this black square down there is the ADCP current. And so this is the vertical is logarithmically spaced. So if you look at the slope here, that tells you something about the viscous stress at the free surface, and maybe there's a presence of an inertial sublayer, some sort of, anyways, I'm not gonna get too much into that, but you can do this over and over and over and over and over again over many different wind forcing conditions and actually get this elusive relationship between the skin velocity, irrespective of tidal currents and Stokes drift, which we won't talk about, and the wind speed, or the friction velocity, which is a little bit like a velocity scale that's related to the wind stress. Okay, And as I mentioned, this is currently under review at JGR Oceans. So if any of you are a reviewer for that, please accept it. Recommended that it be accepted. Okay, so what else can we use this for? Time is dwindling. Okay, so this is one of the most interesting problems, I think, in the ocean, and it terrifies me because I'm not a chemist. The last time I took a chemistry class was 2009. Okay, so this on the left-hand side is a marine radar, X-band radar image. It's a composite image that was formed from the backscattered power from an X-band marine radar. This is a clean part of the ocean, and this is, well, it's not dirty, but there's material on there. There's this gunk that's been excreted by these little filamentous cyanobacteria called trichodesmium that excrete this gel that sits at the surface and has different rheological properties than the seawater. Okay, this is I mean, you don't even talk about biological slicks, oil, mineral oil, crude oil. It's been known for a long time that if you put oil on the sea surface, it will still the waves. This is from the New York Times in 1892, but this is actually newfangled when it comes to, well, I guess I had a picture of Ben Franklin. So Ben Franklin wrote in one of his letters that he had read something by Pliny the Elder that that oil stilled ocean waves, and so he took a teaspoonful of fish oil and put it on a pond, and because of Marangoni forces, this oil was stretched to cover the entire pond, and it suppressed all of the wind waves. Really cool parlor trick. Agnes Pockels, who was an amateur self-taught scientist in the late 19th century, did some really fundamental experiments on the effect of these surface films to suppress waves. Okay, so we made some measurements a couple years ago in the western equatorial Pacific, both in the open ocean and the East Timor Sea, just off the northern coast of Australia. And what we did was we took a research vessel and we did transects across these fronts, where there were these sub-mesoscale fronts where there was convergence of this biogenic stuff. And what this allowed us to do was connect the velocity of our ship relative to the sea surface, which we got from an infrared camera using some velocimetric techniques, to actually the spatial variation in our spectral energy density. So what we could do is look at a region where there was suppression and no suppression and obtain a damping ratio. The damping ratio is just simply the ratio of the spectrum in the unsuppressed versus the suppressed. And so when the value is very, very high, that tells you there's very strong damping. This little dashed line, that we basically said, well, we have a logarithm of this power. So if we take a derivative of that and then perform a least squares fit, we can get this damping coefficient, which you can think of as like an inverse E-folding spatial scale. So as you go further and further into the slick, the wave energy goes down and down and down and down. So it's like this exponential decay strength, essentially. Okay, one use for this damping coefficient, the damping ratio, is the damping ratio is directly connected to the elastic modulus, one of the viscoelastic properties of seawater. And as you increase your elastic modulus, you increase the damping ratio. This is modeled. This is from some fundamental work done in the 1980s by a group of Italians, Lombardini and Cini, not Greg Cini, but a different Cini. But then on here, this violet curve is what we observed, and then the teal one is modeled. We just look at where the peak is, and voila, we can infer the elastic modulus of seawater. And that's a really, really, really hard measurement to make. So I think that's pretty cool. Let's talk a little bit about that damping coefficient. So if we measure the spatial variation of our spectral energy density, and we integrate it, we can get the mean square slope, so the variance in our slope, our measured slope value. So this is tremendous. This is really quite stark to see in the span of 150 meters to drop by a factor of 4 or more. If we just look at that little tiny corner up there, we see that in about 40 to 50 meters, our energy density has dropped by about a factor of 10. And so if I recast this damping coefficient, I take 1 over the damping coefficient, and then I multiply by 1/2 times the natural log of 10. Now this is a characteristic length scale that tells you how long it takes to fall by a factor of 10. And so you can see, after about 40 meters, we fall from the orange is minus 2.5, the dark blue is minus 3.5. And so this tells us that our characteristic length scale for damping at that particular wave number, length scale is about 50 meters. And so we call that D sub alpha. And when we look at the sea surface temperature, so we had a little infrared radiometer on the ship, so we could look at the brightness temperature as we were passing over these features, and we see, the integral length scale for the sea surface temperature features is a pretty close match to this damping scale that we get just from measuring how these short waves evolve as they propagate into a region where there's these suppressive slicks. Okay, I'm going to gloss over this. I guess what's interesting is how variable this is regionally. This is a little bit scary. I like to think that you make a measurement somewhere, it's good anywhere. No, it is good there. So these are coastal measurements, East Timor Sea, this is the Western Equatorial Pacific. There's really very little, there's huge differences in the amount of chlorophyll A and surface active substances, and much higher in the coastal region. But you see that, yeah, at low winds, there are enormous variations in this damping coefficient. This little K to the minus 3/4 power Nike swoosh that I put on there, that indicates the presence of something called Marangoni-Gibbs damping, which is a really cool process. And it's by which surface wave motions, like long surface waves, will give you regions of convergence and divergence, which accumulate surface active substances. And so you have this wave that is propagating like this, that's a transverse wave. You get these then surface longitudinal waves that come into resonance with our free surface waves, and you get this destructive interaction, and that steals energy from the waves and converts it into the mean flow or the turbulence. Anyways, there's not enough time to talk about it today, but this is, I said I'm like a bloodhound hunting for power laws. I was very excited to see that. Okay, we're not gonna get into that. So I guess the big takeaway is coastal regions with really narrow filamentous slicks that are windy and weavy and kind of, so the energy density falls off in a very short order. It's a little bit like a suppressive, like a brake that's being applied to the surface wave field. And then actually this tau sub W is the momentum flux that's being imparted into the wave field. So how much is the wave field taking up from the wind forcing? If you have a coastal region with really low density, stretched out slicks, so stretched out in the span-wise direction, so they're not very prominent, you're gonna have a pretty low, relatively low suppressive effect in contrast to the very tight, spidery, filamentous ones that are high density of surface active substance material. So this was published in Journal of the Royal Society's Interface, multidisciplinary journal last year. So if you're curious, none of you have a camera, I don't want to put in the QR code. People who are watching online, if you don't want to type that name in, you can just take a picture of that QR code thing. Okay, so I think we're just about at time. So I'll put this one graphic that I stole from Hui up one last time and give a plug to anyone who's not here from Tech 411 or who's completed all of their schooling. I am teaching a class in the spring called Dynamics of Air Interaction. We meet 2 days a week, Mondays and Wednesdays, and we will talk about everything from boundary layer theory, Monin-Oblikov similarity theory, how you can relate surface fluxes to boundary layer structure, the growth, development, interaction, breaking of surface waves, and then the consequences for upper ocean turbulence, things like Langmuir circulant. Well, you'll learn about what that means if you join the class. Anyways, please feel free to reach out to me if you want to know more about the class. My final plug, and with that, I will put this slide up and thank you for your time.
We have time for a few questions. If you have any, please raise them.
Yes?
So would it help if you used, instead of ambient light, if you used your own light source? That was where you control the polarization?
Probably, yes. So the question was, would it help if you could bring your own light source? So you could control very carefully, is it diffuse, uniform, unpolarized? In principle, yes, that would help. In practice, it's really hard to illuminate this, you would basically be making all your measurements at night over the ocean, right? And then how do you set up an apparatus where you can supply enough light that's diffuse enough so you're not just by illuminating one facet and not the other, and you're not putting the superstructure that's obstructing wind forcing on the water surface. So this is one of those weird techniques because it's actually easier to implement in the field than in the lab. Because in the lab, you've got to supply your own light source, but actually providing diffuse, uniform, unpolarized illumination is a huge headache. It's really, you have to, basically, it looks like a photography studio. All the diffusing screens and reflectors, and you could, maybe the volume that they have out in LA, you have a bunch of LED, like OLED screens. You just give natural illumination that way. So there are probably some facilities that you could do it right. Maybe Biosphere too. But in practice in the field, I've seen some people try to do it, and it has not turned out well.
So it would help, but it's just too hard to do.
I think in practice, it would be too challenging. Now, I did not really mention a way other than the method that I proposed. There are techniques that involve radiative transfer modeling. So basically, Monte Carlo simulations of scattering under the water and in the atmosphere. And it's extremely computationally expensive and time consuming, but you are able to infer the polarization state of the sky leaving radiance and the upwelling. It just requires, you're making measurements in multiple different bands. So you get your UV, your red, red, green, blue, near infrared. And then by assumptions on how each of those is transmitting through the atmosphere and scattering in the subsurface, you can back out what that Fresnel curve is. That's probably the best way to do it. There's another kind of quick and dirty way that we have two cameras, one narrow field of view, one wide field of view. The wide field of view is giving us a sort of empirical in situ Fresnel curve that takes into account everything. All the physics is just sort of bundled in there. And then the narrow field of view is making our measurement for us. And I think that's the one that has the most legs to it. But to answer your question, probably the best way is to supply unpolarized light, but in practice, I've not been able to get it to work. Yes?
So you did a lot there. Do you think if you would get the same information, would it be worth doing your polarimetric light source cameras if you just had a LiDAR set up? Would you even bother doing that? Or do you think you get the same information out of having a LiDAR field of a large, similar, comparable area?
Yeah, it's a good question. So I think if you have a line scanner that can just go back and forth and you fly a fixed wing aircraft or a quad rotor, there's a group out at Scripps. It was Ken Melville's old group, now it's Liplanane. It's called the MASS, Modular Air Sensing System. They have a scanning LiDAR that's able to get water surface elevation as a function of space. But it's a little bit like SAR because you just sort of give this, it's a push broom imager, really. And so you're getting this frozen snapshot in time and you're moving it through. And so you can, as long as it's moving fast enough, like a fixed wing aircraft, you can get a nice frozen field of the water surface of the geometry. But you're not getting the temporal development. If you had a scanning LiDAR on a quad rotor that was hovering, maybe, but then of course, I mean, I've been banging my head against the wall trying to get an airborne system to work for a couple of years now. It's very hard, I mean, obviously, with a polarimetric camera on it. With a LiDAR though, just imagine a tenth of a degree, a really good like dual antenna GNSS INS system where you've got like a tenth of a degree accuracy on a UAV. And now imagine that you're 100 meters, 200 meters off the water. So your spatial error in all these points is going to be jittering for each one of them. I just think having a global, like a CMOS, like a global, basically not a rolling shutter, a global shutter CMOS, where you get all the information all at once. There's no jitter, there's no lag, there's no spatial like registration errors. I am a big fan of LiDAR. There's a Tech 797 group that I'm advising that's putting a scanning LiDAR, an automotive scanning LiDAR on a buoy, but it gets us 1 meter by 2 meters, give or take, maybe. So, I mean, who knows? If that works, I'll just hang up the polarimetry stuff and retire. Not retire, but retire this side of things. I think that it's probably going to be what's the right tool for the job? Maybe we want to get the really fine scale waves, so we use this. Maybe we get the intermediate scale waves from the LiDAR, and that does that well enough. It's very unlikely that there's one panacea. There's like one technique that just gets everything. I was trying to do that a little bit by extending the technique, and it gets the long waves okay. It gets the short waves pretty well, depending on the illumination. But yeah, the LiDAR, what's nice about it is it's just speed of light, time, distance to target. It's so simple, which makes it so attractive. I mean, like, there's not really many ways for really like crippling error to enter into the system, which I like. So I like LiDAR. I like light. Any sort of light-based technique I love. So sound is good too. I'm not gonna leave the acousticians out, I guess. Yes.
So to me, the concept of the polarimetric cameras is kind of new. I'm just kind of curious, like, is this sort of are these the measurements these cameras are generally used for, or is this sort of you're taking something out of a completely different field and applying it in? Like, what are they usually used for?
Great question. I like to imagine that Sony put hundreds of millions of dollars in R&D because they cared about my research and they wanted it to be more efficient. But I think it's used for defect, like inspection of chips. They have this little camera, and also there's some scary military applications for it too, but we won't get into that. But yeah, if you have an assembly line, you can detect the most minute aberrations in the orientation. So if there's a tiny scratch on something, it'll show up in the degree of linear polarization. So it's great for quality control, like process engineering. That's probably the main reason. But then for like object detection. You know, like if you've got a camera that can give you S0, S1, S2, then you can, you know, maybe you can it'd be like glint removal. It can be detection of objects that are very different from other objects. I mean, there's so many different applications for polarization beyond just surface kinematics inference. But like a lot of the fundamental work was done in the 19th century by Stokes, Fresnel, Rayleigh. I mean, like these old dead names. But then there was a little bit of a renaissance in the 80s when people were using, now there were cameras where you could actually put a polarizing filter, the optics were good enough. And so I would say the late 80s when it started, but then the technique was first used for ocean waves about 15 years ago, 17 years ago. Actually, I'm going to bore you with the story since I've got a semi-captive audience for the next 30 seconds. My first day interviewing for graduate school, I walked into my soon-to-be advisor's office, and on the floor was a Pelican case with the camera, and on top of it, a printed copy of the paper in the measurement science and technology that told you how to use it. And he didn't know about any of it. He didn't understand. He wasn't the expert on it. He's like, I bought this camera, and I printed out this paper, and I want you to learn how to use it for your PhD. So this has been a 13-year journey of ups and downs, but a lot of fun. And yeah, so that's it.
If there are any questions, we'll thank our speaker one more time and